Hi everyone, my name is Natalia Matiuto. I'm a PhD candidate in Dr. Jiang's lab and here in the Department of Surgery at Northwestern. And today I want to tell you a story about what happens when the most basic function of our body, healing, fails. Think about the last time you got a cut. Maybe you were chopping vegetables late at night, you were tired, obviously the knife slipped, you got a cut. Nothing crazy happened, it was painful, maybe uncomfortable, but you just put a Band-Aid on it and you just went about your day. So this is the reality for most of us. Typically wounds heal within 7 to 10 days and nothing crazy happens. But for 7 million people in the US suffering from diabetes, these wounds don't heal. Instead, they linger for weeks or months, and in severe cases, they lead to amputations. And here's why it happens. In patients with diabetes, the changes in metabolism cause poor blood function, impaired immune function, and low cell energy levels. And this problem is more than just painful and dangerous, it's also extremely expensive. It costs the US healthcare system about $25 billion a year to treat these wounds. In fact, every 30 seconds, someone somewhere in the world will lose a part of their limb due to diabetes. And these losses are preventable. They mostly happen because the wounds don't heal, and our current treatments don't work. So here's why it happens. Our cells rely on this small organelle called mitochondria. You might remember it as the powerhouse of the cell. And in diabetes, these mitochondria don't work properly. Think about trying to restore your house from a storm, and the workers are there, the plans are there, but your instruments have no batteries in them. So this is the reality for patients with diabetes. And here's what my research does to help with that. So what we're trying to do is to deliver healthy donor mitochondria to the wound, to improve wound healing, to deliver that much needed energy to the wound, to jumpstart the healing and decrease inflammation. We do this through a process called mitochondrial transplantation. And while it sounds daunting and complicated, it's pretty simple. So let me walk you through this. So here's how we do it. It starts as simple as just drawing a blood from a patient, from a healthy donor patient. We then look for a specific cell type that will be transformed into the donor cells. This process is similar to embryonic development, when you can get a variety of different cell types from a single cell. Then we isolate mitochondria from that. Then we would embed this mitochondria in the form of a gel to be applied topically to the wound, to bring that much needed energy back to the cells, to the tissue, to jumpstart the healing and essentially heal deep cuts to a fully healed tissue. And the results of our animal studies are really promising. Here you can see a picture from our pilot animal study where we created 2 circular wounds on the back of a mice. They're the same size, 6 millimeter. The wound on the left was a control, untreated control, and the wound on the right was treated with our mitochondrial transplantation therapy. By day 3, you can see some difference. You might see that the wound on the right seems a little more close than the wound on the left, but by day 7, you can see a stark difference where the wound treated with mitochondrial transplantation therapy almost fully closed. But this research is more than just building animal models or developing a one-off treatment for diabetic wounds. What we're building here is truly a platform technology that can be applied to a variety of different diseases where mitochondrial dysfunction is present. One of the examples include heart failure, and this is actually something that was already done in Boston Children's Hospital, where the direct injection of mitochondria into a cardiac tissue helped save lives of 14 kids. Another example includes neurodegenerative diseases. If you think about stroke or Alzheimer's disease, where cells are desperately craving this energy, mitochondrial transplantation can also help with that. And finally, aging. In aging, cells are constantly lacking energy to restore or regenerate, and this is where my research can also help. So we're now at a very early stage of the discovery of this platform technology. We are trying to investigate the effects of this transplantation therapy and see how it works in vitro in cells before we progress to actual development of preclinical models in animals. And this work done in animals further moving forward can be used to further to provide a good, strong basis for us to file a investigational new drug formulation or filing with FDA. And that work, that filing, will essentially establish the regulatory basis for us to go with the first-in-human clinical trials. So you can see that this work, it takes a lot of work and takes a lot of time, but what we're building here is more than just cells and animal models. What we're building here is truly a platform technology that can help save lives, prevent amputations and injuries. Because when energy fails, healing stops. And we are working hard on bringing that energy back to the cells, one cell at a time. Thank you.